Hi guys, we're going to pick up with covalent bonds. Now, covalent bonds are when nonmetals share electrons to complete their octets. And remember, octets are only filled with valence electrons. These are the outermost shell, okay? And they are shared between the two atoms to achieve the stability of a noble gas. The simplest one that we can form is between two hydrogen atoms. Now, in this case, the closer the hydrogens get together, the more the attractive forces between that positive nucleus and the negative electron. And when they get close enough for the attraction to occur, a single bond forms between the two of them, and they share one pair of electrons and form a simple covalent bond. This is just showing you again, when they're far apart, no attraction happens. However, the closer they get to each other, the positive nucleus attracts a negative electron, and then the molecule bonds together, sharing their pair of electrons. We like to show these covalent bonds using electron-dot formulas. If we're just looking at an example of fluorine, now fluorine is in group 7, so it has 7 valence electrons. It will bond to itself. Now what it does is they will each share one electron to complete their octet, and they form a covalent bond. Just like what we've seen before with hydrogen, the same thing happens, that their negative electron is attracted to the positive of the nucleus, the positive of the protons in the nucleus. And they share a pair of electrons here, okay? And it's easier for us, instead of drawing all these dots around, anytime we share a pair of electrons, like a bonding pair, that they're shared between the two of them, we draw that using a line. And every other electron that's left, we call them lone pairs. And we show them by themselves. They're paired up and they don't react, they kind of just hang out together. There are a total of 7 elements that will actually appear in nature as what we call diatomic molecules. So they covalently bond to themselves. Now these include hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. You do not actually need to know these, but it's just one of those cool little factoids about nature. Now the big important thing that I do need you to know right here is that the number of covalent bonds of a nonmetal forms is usually equal to the number of electrons it needs. Okay, so in other words, the way to put this is because everything in group 7 has 7 valence electrons, it only needs 1 electron to complete its outer shell. Therefore, it will only make 1 bond. Now, ones in group 6, elements in group 6, these have 6 valence electrons. We need to get a total of 8. So therefore, they can make up to 2 bonds. And ones in group 5, they need 3, so they can make up to 3 bonds, and those in group 4 can make up to 4 bonds. Now these are just showing you the electron-dot formulas for these covalent compounds, and we're going to go over how to draw them in a little bit too. But basically, anytime we can show them just using the dots, but that gets slightly confusing. So what we usually do is show them with the bonds and drawing them in as lines. So all the lines are the shared pairs of electrons, and anytime you see 2 single dots by themselves, so they're considered lone pairs. So how do we actually draw these? And let's get drawing them and practice drawing them. The first thing you have to do is always determine the arrangement of the atoms. And in that case, the central atom is the one that can make the most number of bonds. The other thing we're going to do, and then we put the other atoms around it, is that we determine the total number of valence electrons we have to work with each other. And then we attach each bonded atom to the central atom with 1 pair of electrons to start with. And then we fill in the remaining electrons using single or multiple bonds, so we complete octets. So let's just start with our first molecule, which is NH3. Now, with NH3, we have nitrogen, which is in group 5. So it has 5 valence electrons, and there's just 1 of them. Because we have H3, this subnote here means that we have 3 hydrogen atoms. So 3 hydrogens, and they're all in group 1, so they all have 1 valence electron, means we have 3. So we have a total of 8 electrons to work with. And I'm just going to try to make this slightly bigger if I can. So we want to know which is the central atom. So the central atom in this case is the one that can make the most bonds. Hydrogen can only make up to 1 bond. Nitrogen can make up a total of 3. So nitrogen goes in the center. Now we have hydrogens. We have a total of 3 hydrogens, so we're going to put them around the nitrogen. So now we've surrounded them. The next thing we're going to do, because we know we have 8 total electrons to work with, I'll put my 8 up there, we're going to bond the elements together to start with. So we'll put 1 pair here. So we'll take away 2. That gives us 6. We'll put another pair in here. We'll take away 2. That gives us 4. And we'll put 1 more pair here. Take away 2. That gives us 2. Now currently we have to fill the rest of the electrons in. These last 2 have to be put in. Well, first let's see who's complete and what's happy. Remember, hydrogen is complete and happy with just 2 electrons, okay? So this hydrogen is all set, this one is all set, this one is happy. Nitrogen, on the other hand, needs a total of 8. Anything other than hydrogen always needs 8 electrons. So we have 1, 2, 3, 4, 5, 6. So the last 2 will go as what we call a lone pair above nitrogen. And then we're at 0. We've used all of our electrons. So this is how you would draw NH3. Another alternative way to think of this is to think of nitrogen as itself. And if you get confused with what is going to be the central atom and make the most bonds, think of nitrogen. Nitrogen itself is in group 5. So if we draw nitrogen in group 5, we first start putting in the electrons singly. There's 4. And then we double up. That's what an element in group 5 looks like nitrogen. Hydrogen is in group 1. It only makes 1 bond. So it looks like this. So if it helps you, you could technically draw out the atoms like this and then go, oh, hey, look, I have 3 hydrogens. So let me draw my 3 hydrogens in with their single bonds. And then you can connect the 2. So they're going to share this one, and that. So that's kind of another alternative way of drawing them. But just giving you an idea here, okay? So we're going to move on. I'll try to shrink this a little more. Hopefully it hides it. So again, like we said, we're going to attach each bonded pair with a central atom with a pair of electrons. And then we bond the 2 and we put the 2 remaining and making sure everything has a complete octet. So now let's try CCl4. So CCl4 is carbon tetrachloride. Not that you need to know the name yet, but we'll get there. We'll make this bigger. Bear with me for a minute as I try. That doesn't want to dry. I'll just go like this for now. Okay, so CCl4, we're dealing with carbon and chlorine. We have, if we're looking and making our list for CCl4, we want to know the number of atoms, and then we're going to do the group number, and then how many valence electrons it has, and then how many total electrons we have to work with. So in C, remember we're working with CCl4. That means we have 1 carbon, 4 chlorides or chlorine atoms. In this case, carbon is in group number 4, chlorine is in group number 7. That means the valence number of electrons here, okay, are 4 and 7. However, we want to know the total number, so we have to multiply by the number of atoms. So this would be 4 times 1, which would give us a total of 4. And this would be 7 times 4, which would give us a total number of 28. And then if we're adding together our 28 plus 4, we'd get 32 electrons that we have to work with. Knowing that we have 32 to work with, let's think about what they look like. Carbon, again, group 4, looks like that. Chlorine is in group 7, so 1, 2, 3, 4, then we'll double up, 5, 6, and 7. Oops, I didn't mean to hit that camera, I apologize. But when we start talking about anything in group 7, remember, group 7 was a special group. It can only make up to 1 bond. So this has a space for 4 bonds. Here we only have a space to make 1 bond. So our central atom is going to be carbon. So we'll put carbon in the center, and then we'll put our 4 chlorines around it. Now what you have to do is just bond the 2 together initially. So remember, we're going to take our total number of electrons here, and we're going to start bonding them to the central atom. So let's put in 2 here. So that gets us to 30. We'll put in another 2 here. That's to 28. Another 2 would what? Get us to 26. 2 more should get us to 24. And now we have to fill out the rest. We have 24 electrons that we have to distribute through everything else. So we want to make sure every atom has a total of 8. Right now, carbon, 1, 2, 3, 4, 5, 6, 7, 8 is all set. So we don't really have to worry about it. We'll put a little check mark next to it. But these guys are not happy. They're not filled. So let's start filling with 1 chlorine first, and we'll go from there. So we're going to put in 1, 2, 3, 4, 5, 6, and then that would be 7, 8. So we're getting away 6. So that should get us to 18 here. Let's do another 6. That'll get us to 12. We'll do 6 more. Get us to 6. And then our last 6 right here gets us to 0. And if we're checking, now each chlorine has a total of 8. So that would be CCl4. There we are. You determine the central atom, remember, the one that can make the most bonds. We determine our total number of electrons, and then we connect them together again, and then we draw them in. So there are only a few exceptions to this octet rule that you have to pay attention to, and the main thing is that hydrogen only requires 2 electrons, and the other 2 that might come up, however, it will not come up in this course, are boron and beryllium. Boron only requires 3 electrons, and beryllium only requires 4. On the other hand, though, we do have some cases where we can get what we call expanded octets. Now, this is what we really see in phosphorus and sulfur, and sometimes we can see it with the halogens with chlorine, bromine, and iodine, where they can have upwards of more than 8 electrons, up to 10, 12, 14. And these are only under special circumstances will this occur, but don't worry. The only thing you just have to remember right now is that hydrogen only requires 2 electrons. Everything else requires 8. Now, you might want to know the difference, and it's good to know the difference. You will need to know the difference between single and multiple bonds. So in many of the covalent compounds, we are sharing at least 1 pair of electrons, but sometimes we share 2 or 3 pairs of electrons to complete their octet. And that's how we get to the idea of a single, double, or a triple bond. In a single bond, we're sharing 1 pair of electrons. In a double bond, we're sharing 2. So this would be a total of 4 electrons that are shared. And in a triple bond, we're sharing a total of 6 electrons total. So let's actually see one and how it will actually happen and play out. And why would this happen? A good example here would be CS2. And in this case, the reason why we share multiple pairs of electrons is because the number of valence electrons between the 2 of them wouldn't be enough to make single bonds. So they're going to have to share multiple pairs to actually be happy. So if we look at CS2, the first thing we're going to talk about is what is considered our central atom. So remember, carbon is in group 4, sulfur is in group 6. So I'm going to just maybe shrink this a little bit as we go through. So we have our carbon, our group 4, and sulfur is our group 6, okay? What ends up happening here, that's CS2, because carbon is in group 4, so let's think group 4, we have group 6. This one is going to be our central atom, so we're going to put it in the center and we'll put sulfur on each side. If we were going through with the arrangements of how many we have with CS2, by now you know that the group number is equal to the number of valence electrons. So here's our C, here's our S. We're going to put our number of atoms here. Then we're going to go number of valence electrons, and then we'll get our total electrons here. I have 1 carbon, 2 sulfurs. With carbon, it's in group 4, 4 valence electrons. With sulfur, it's in group 6, a total of 6 valence electrons. Now, if we want to know the total number, it's the number of atoms times the valence, so this would be 4. And here we would have 2 times 6, that's 12. Add the 2 of those together, we get a total of 16 electrons that we can work with. The first thing we're going to do is bond the 2 together, right? So we'll put 1 paired share between the 2 and another paired share between the 2. So that's a total of 4 we've used. Take away 4 from 16, that leaves us with 12 to figure out. Do you think we could make everything happy with just the remaining 12? Well, we could start filling. So let's start filling with the sulfur first. So we need a total of 6 over here. 1, 2, 3, 4, 5, 6. That gets us to 6. And on this sulfur, if we're filling from the outside in, we would need another total of 6. 1, 2, 3, 4, 5, 6. Okay, now we have 0 left, but the problem is sulfur's happy here, this one's happy, but carbon is missing a total of 4 electrons. So this wouldn't work because carbon isn't happy. So what ends up happening, and we can kind of see it here, if we're looking up here, remember carbon has 4 electrons to begin with, it's actually going to form a double bond, okay, to make itself more stable. So let's get into trying again. I'm just going to move on with this. So we're just going to show you that it just doesn't work because we're not complete. Carbon is missing something, so we have to form a double bond and share. So what ends up happening is we can donate a pair from here, and we can donate a pair from here to share to make them happy. And it looks like a football field here. But if we're looking at it again, in this case, so we have our carbon atom, we have our sulfurs, and we're sharing. If we thought of it this way, that here's our carbon with its 4 electrons that it has on its own, and here is sulfur with its 6 electrons, and here is another sulfur with just its 6 electrons. You can kind of think of it like this. Kind of, they're going to share these 2 to make themselves happy. So we're going to form double bonds between. Each one is kind of donating a pair, and we're forming a double bond. So to make it look cleaner when you're drawing, it would look like this. Okay, so we're sharing a total of 4 electrons here and 4 electrons there. And everybody is happy because now this sulfur gets 8. 1, 2, 3, 4, 5, 6, 7, 8. This sulfur gets 8. 1, 2, 3, 4, 5, 6, 7, 8. And carbon has a total of 8. 1, 2, 3, 4, 5, 6, 7, 8. So we're happy in this state here. Now, in some cases, you might see triple bonds form, and triple bonds we'll see like in the form of nitrogen. And nitrogen is in group 5, and in this case, each nitrogen atom is going to share 3 electrons total, and they'll complete their octet here, that way. And that's why it's also known as a diatomic molecule. It's one of those 7 we talked about earlier. But we share a triple bond. There are some cases in which we have what we call a resonance structure. And these are special incidences which we'll see with double bonds. And it's the fact that the double bond can be formed in 1 or more atoms, and sometimes they switch spots between the atoms. And so it's just a rotating location of where that double bond is. And we really will see, well, a good example of this is the one coming up. And I know this is kind of a big concept to get, but it's when you have 2 or more electron-dot formulas for the same arrangements of atoms. So it means that the double bond could have been present on one of the other atoms, okay? And in nature, it just means that that bond would actually move, so the location of them is different. So the big example of this is sulfur dioxide, SO2. And this is one that I would like you to feel comfortable with drawing or being able to draw SO2, because this might come up as a nice exam question, being able to draw it. Now, for sulfur and oxygen, all of these are located in group 6. They all have 6 total valence electrons. So because we have 3 of them, we have a total of 18 electrons to put between the 2 of them. In this case, what you're going to determine the central atom, we're just going to put it the one that is the single. So we'll put sulfur being central as it's coming first in the formula, and we'll put the oxygens on either side. Now, if you were to attach each bonded pair of atoms to the central atom, we would do a single bond each, and then you start filling. You now have to fill in the remaining of the atoms. But the problem is now, if you fill in the remaining 14, sulfur still isn't happy. All the oxygens are happy, but sulfur is missing 1 pair. So it can take this pair from this oxygen from on the left over here, or it could take it from the oxygen on the right. And in nature, it's going to flip-flop between which oxygen it chooses from. And that's known as resonance, okay? Because it could go from either side. So with that being said, let's think of FNO3 or FNO2s. I shouldn't have a 3, there should be a 2. FNO2, it's rocket propellant. And in this case, there's 2 resonance structures possible for this one. So one is shown below. What could the other one be? So you have to remember, and let's kind of think about this one, and we'll draw it out. We'll try to draw it out. But here's our FNO3, right? You have fluorine, nitrogen, and we have our oxygen. We have one that has a double bond, one that's a single bond, and then our fluorine. Here's the thing you have to remember. It's not possible for fluorine to make a double bond. So fluorine is out of the question of where that other double bond could go. However, there is another oxygen. And because there's another oxygen, one day could mean that this pair is shared instead of one of these. So the other resonance structure that is available, that's why we're going to put an arrow back and forth, meaning it goes back and forth between these 2, will still have fluorine by itself, because that's in group 7. It only makes 1 bond. But in this case, this oxygen is going to be sharing the other lone pair. And it's just going to rotate back and forth between the 2. Now, I know this is a little difficult, and we'll talk about it again. And we'll keep kind of hitting home. But let's again just think of SO2, and let's try to draw SO2. So with our sulfur dioxide, SO2, if we went through, remember, these are all in group 6. So we're going to have a total of 6 plus 6 plus 6, so 18 valence electrons to work with. Sulfur is going to go in the middle, and then we're going to put oxygens on either side. We're originally now going to start bonding together. So we're going to put one pair here, one pair here. So we're going to take away 4 and give ourselves 14. We now have 14 electrons to disperse between the others. So let's start over here with this one. So we'll put in 1, 2, 3, 4, 5, 6. We'll get rid of that 6, and that gives us a total number of 8 to work with. Now the problem is, if we were to just put in 8, right? I can put 6 here and 2 here. So I'll put in 2, and then we'll put in my 6. Again, that's great. I've now gotten rid of all 8, except that sulfur is not happy, it's missing 2. So it's missing 2 electrons. It's an unhappy sulfur, not happy at the moment. What we have to do is we have to borrow another pair of electrons. We can either take it from this oxygen, or we could take it from that oxygen. And that's what it means to be a resonance structure. So some of the time, it's going to take it from this oxygen, and the other half of the time, hence the arrow forward and back, it's going to take it from the other side. That's what it means to be resonance. Okay, so it's going back and forth which side it's choosing from to get that other paired share. Now let's just work on switching gears. We kind of went over drawing, so let's talk about naming. So naming of covalent compounds is different than naming of ionic compounds. In ionic compounds, we didn't mention the total number of atoms that we had. We just named them as the metal and then the non-metal. When we start talking about covalent compounds, we're going to do the non-metal first by its whole element name, the first one we see in the formula. Then the second non-metal is going to be the first syllable followed by "ide," similar like we've done before, except that in this case we use prefixes. And the prefixes are going to tell us how many elements in each compound we have. So here are the common prefixes we use. 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, 10 is deca. So if we're looking at some examples here, CS2 is carbon disulfide, CO2, carbon dioxide. If we just had CO, it would be carbon monoxide. NO is nitrogen oxide. Okay, you don't necessarily have to put the mon in front of it. N2O is dinitrogen oxide. SiO2 is silicon dioxide. SO2, sulfur dioxide. SF6, sulfur hexafluoride. So just some names for you. But again, remember we're going to go with the first nonmetal by its whole element name, then the second nonmetal using its first syllable followed by "ide, and then we'll add any of the prefixes in. So if we're looking at SO2, let's take it apart. S is sulfur, then we have oxygen for O, so that becomes oxide. Because there are 2 of them, it becomes sulfur dioxide. And it's just giving you the idea here. So let's try to name this one P2O5. So if we're taking P2O5, let's think. P stands for phosphorus. And the O stands for oxygen, which means it becomes oxide. Now we do have prefixes we have to put in. The 2 means di, so we'll have a diphosphorus. And then the 5 means we have to use, I didn't give myself enough space here, penta. So it becomes diphosphorus pentaoxide. let's name the rest of them. We have SiCl4 and Cl2O7. So take a moment and try. But Si is silicone. 4 means tetra. And Cl is chlorines that becomes chloride. If we're looking at Cl2O7, the 2 means di, and Cl is chlorine. So don't put chloride there, don't shorten it, use its full element name. And then 7 is hepta, Hepta, and O is oxygen, so that becomes oxide. So there they are for you. Let's try drawing them now. So we did some naming, now let's do some drawing. Drawing, we're just going to take the name and take it apart. Like if we're looking at sulfur hexafluoride, S-sulfur means S, hexa means there are 6 of the fluoride, which is F. So it would be SF6 with a subscript. So let's try writing dinitrogen trioxide. So dinitrogen trioxide in this case, so nitrogen is N, oxide is O. Dinitrogen means there's a 2 for nitrogen. Trioxide means there's a 3 for oxygen, so N2O3. And then there it is for you. The last thing we're going to cover, and then we'll do eventually some more examples in the problem sets, so just look for the little problem videos on that one. We want to talk about electronegativity. And this is a measure of an atom's ability to attract bonding electrons. And it increases from left to right. So going across the period in a periodic table, electronegativity will increase. And then it decreases going down the group. So the further down you go, the lower you go, and the bigger the atom gets, the less or the lower the electronegativity is. So the highest electronegativity is in the nonmetals, and it's highest for fluorine. Now this actually makes sense, because if we're thinking about the periodic table, all the way in the upper corner, remember this is the ability of an atom's ability to attract a bonding electron. Well, metals are going to have low electronegativity because metals give away their electrons. They don't attract anything, they give away. Nonmetals, on the other hand, always gain, or they attract electrons. Because remember, with those nonmetals, they really want to complete that outer shell. And if we're thinking of fluorine, all the way at the top, so the uppermost right-hand corner of the periodic table is going to have the highest electronegativity. These are the smallest molecules, so that means that their positive center is the closest to be able to pull in that electron. So here it is. These are just giving you some electronegativity values. This little chart I will have available for you if I ever ask you a question on an exam, so you'll be able to know the notes. But there is fluorine right there, 4.0, with its highest value. Okay, and all these metals are very low, because remember, these like to just lose their electrons. They don't gain any electrons. Now, because of electronegativity, we can talk about a few types of bonds, and electronegativity can actually dictate the type of bond that occurs. And we can classify all the bonds between elements as either nonpolar covalent, polar covalent, or ionic. So how equal we are either sharing or whether we are just completely taking the electron. So in the case of nonpolar covalents, these are going to be where there's an equal share of electrons. Polar covalent means there's some partial charges or dipoles. These are an unequal share of electrons. And ionic, we formed ions because we've completely transferred one electron to the other. Very, very unequal. So let's think of what is happening where. Nonpolar covalent bonds. This occurs between nonmetals only because covalent bonds are only between nonmetals. This is the equal or almost equal sharing of electrons, and there is very little electronegativity difference. It ranges from 0 to 0.4. So here are examples of some atoms bonded to each other and their electronegativity difference. So they result in what we call a nonpolar covalent bond, just an equal share of electrons. Polar covalent bonds, on the other hand, are unequal shares. That means that there are more electrons usually associated with one than the other. And because of that, there's going to be what we call dipoles or partial charges. So if we look at examples of like oxygen bonded to chlorine, or if we had oxygen bonded to water, we're going to see what we call polar covalent bonds because we have high electronegativity differences from 0.7 all the way to 1.7. Like in the case of water, what we mean by an unequal share. So equal shares, let's look at chlorine bonded to chlorine. Here are the electrons. The atoms are about the same size, and the electron cloud is about the same size around each one. If I have water, okay, here is water. Right now, I have a very unequal share. The majority of the electrons are all around oxygen. So this means this is going to have what we call a partial negative, and hydrogen is going to have a partial positive. So these are called dipoles, these partial charges. And the majority of the electrons are all around one atom. And because of that, it's considered a polar covalent bond. And remember, these only happen again with nonmetals because covalent bonds are only possible with nonmetals. So here we are showing basically an equal share versus an unequal share. And then ionic bonds occur between a metal and a nonmetal, and these are resulting in a complete electron transfer, and we're forming ions. This is a large electronegativity difference of 1.8 or more. So you are responsible for knowing the difference between nonpolar covalent, polar covalent, and ionic bonds. You'll have to know those for the exam. And you should know the electronegativity difference. So here, just giving you some more examples. So if I ask you to look at the difference here and use the following, I want you to use the chart. This would be a very good example of what you'll see on an exam. I want you to take the difference and tell me whether these are nonpolar covalent, polar covalent, or ionic bonds. So the bond between K and N, or potassium and nitrogen. First off, here's potassium as a metal all the way down here, nitrogen as a nonmetal. That should be your first clue. You don't actually have to go any further. Anytime we cross between a metal and nonmetal, this bond is ionic. If you also did subtract 3.0 minus 0.8, again, you're going to get to that 2.2, so therefore you'd be ionic anyway. ClCl, the difference between these two is 0, so therefore it is nonpolar covalent. And then BCl, we're still in nonmetals. This metalloid is still to the right of the step, so it behaves as a nonmetal. So between B and Cl is only a difference of 1. This becomes a polar covalent bond. The last thing we're going to discuss, you've almost made it to the end, are just the shapes of molecules. All molecules have a three-dimensional shape to them, and this is the number of bonding groups and lone pairs around them. It helps them form what we call this VSEPR theory, or valence shell electron pair repulsion. So anything that is negative and like charges will repel each other. So every pair of either another atom and the electron groups associated with that, or a lone pair of electrons, are going to repel each other and try to be as far apart as possible. And because of that, it creates a certain bond with a molecule. So we're going to go over a few examples of shapes, and then I did put up on Moodle, there is a lovely little simulation with PHET, P-H-E-T, which you can use to go through and look and explore these shapes a little more in depth. So VSEPR theory, just know that these are going to arrange, the electrons in the central atom are going to arrange themselves as far apart away from each other to have the least amount of what we call repulsion or steric hindrance. And because of that, we can use that to predict the molecular shape associated with the molecule. Anything that just has two electron groups is considered linear. And remember, we only really see this in the exception to the octet rule, like Be, beryllium. So it's a very linear shape in geometry. EF3 is boron trifluoride. So if we're looking at this one, in this case here, again, this is another exception to the octet rule. You don't really have to worry about these shapes, but I just want to introduce you to them. This is considered trigonal planar, and all of the groups are equidistant apart from each other at 120 degrees. Now, this is where we're going in. From this point on out is what are the shapes that I would really like you to have an idea about, because these are the ones that we're actually going to see in the molecules that we're using and making, we're dealing with in the human body. In this case, SO2, or that sulfur dioxide, sulfur has 3 electron groups total. It has 2 electron groups that are associated with oxygens and 1 lone pair. Anytime we have a lone pairs are basically invisible to the eye, so they don't always show up, but they do act as a whole nother group in bonding. So in this case, we're looking at this shape, we are going to see almost the same as 120 degrees. It's a trigonal planar shape, okay, that trigonal shape that we saw before. Except because we don't see this lone pair, it's invisible to our eyes, it just looks like the molecule is bent. So this would be considered a bent shape of 120 degrees. If we're looking at things that have 4 electron groups, so starting with anything bonding to carbon, now we're going to use what we call a tetrahedral arrangement, and there are different associated geometries with this tetrahedral arrangement. All of the bond angles in a tetrahedral are 109 degrees apart. And there's just a certain wedge dash notation. The dark line, that's solid. The wedge means that it's coming towards you, and the dash line means that it's going away from you. So it makes the shape, when you go 109 degrees apart, to be a complete tetrahedral, okay? Almost like a little pyramid if you look at it this way. So if we have 4 electron groups, no lone pairs, just 4 electron groups, we have a traditional tetrahedral. Now, if we have something like NH3, this one has 4 electron groups, except that it's 3 electron groups, okay, and 1 lone pair. And because it has a lone pair, this one is invisible to the eye. So when you look at the molecule, you don't see what's on top in that tetrahedral, you only see this shape down here. And we call this shape, where you just have those 3 groups still 109 degrees apart, this is considered what we call a pyramidal shape. So this is pyramidal. You could also call it trigonal pyramidal or just pyramidal. The last one we'll talk about is when we have 4 electron groups and we have basically 2 electron groups and 2 lone pairs. And when we see this shape, we can't see the lone pairs. Remember, they're invisible to the eye. They're still 190 degrees apart, but instead of being like bent at 120, this is now a bent molecule at 109 degrees. So the shape is bent. These are just giving you the summaries. The big ones I want you to know, you can know SO2, that 120 degree bent one is possible. Don't worry about the other ones. I would like you to focus on the tetrahedral. It's the plain tetrahedral by itself when you have 4 bonded atoms. The trigonal pyramidal when you see 3 bonded atoms and 1 lone pair. And a bent molecule when you have 2 bonded atoms and only 2 lone pairs. So with this, you can learn to draw and kind of predict shapes. So if I just asked you to just predict the shape of NF3, so nitrogen triofluoride, remember here we have we have 4 total groups. That automatically means we're in a tetrahedral arrangement. Because we have 3 atoms and 1 lone pair, this means the 3 atoms puts us at a trigonal pyramidal, okay? So we would be at a trigonal pyramidal shape. And that is it. You made it to the end of part 2. What I'll do now is put up some videos for you as well on how to just name and draw these a little further.